Imagine a production root key that should never belong to one person, one laptop, or one backup drive. You want any three trusted people to recover it together, but any two people should learn absolutely nothing. Shamir's secret sharing gives exactly that threshold behavior using one idea from algebra. Hide the secret as the y-intercept of a random polynomial, then hand out points on that polynomial as shares. The threshold comes from a basic fact about polynomials. 2 points determine a line, 3 points determine a quadratic. In general, t points determine a polynomial of degree t minus 1. So if we want a 3 of 5 scheme, we use a random quadratic. Any 3 shares pin down the quadratic and reveal its intercept. Any 2 shares still leave many possible quadratics with many possible intercepts. Before worrying about implementation details, the encoding idea is just polynomial algebra. Choose a threshold t and build a polynomial of degree t minus 1. The constant term is the secret. Every other coefficient is chosen uniformly at random. Then evaluate the polynomial at distinct non-zero x values. Each participant receives one pair. Their x identifier and the value f of x, the point at x equals 0, is never distributed, because that point is the secret. Next, we will put the same idea into arithmetic that computers can do exactly. For an actual cryptographic scheme, ordinary real number curves are the wrong setting, because rounding errors and approximate arithmetic would be disastrous. So we keep the polynomial idea but move every number into a finite field. In this toy example, the field has 17 elements, so after 16 the numbers wrap back to 0. Addition, multiplication, subtraction, and division are exact, as long as the modulus is prime. This is what makes interpolation reliable. Here is a complete toy example. Work in the field modulo 17, set the secret to 5, and use the quadratic f of x equals 5 plus 3x plus 2x squared. Evaluating at x values 1 through 5 gives these 5 shares: 10, 2, 15, 15, and 2. The repeated y values are not a problem. What must be distinct are the x identifiers. Now suppose an attacker sees only 2 shares, such as 1, 10 and 2, 2. Those 2 points do constrain the polynomial, but not enough. For every possible value of the secret at x equals 0, there is some quadratic that passes through the same 2 known shares. Because the random coefficient that remains hidden can compensate for any chosen intercept, the 2 shares do not make one secret more likely than another. When the threshold number of shares arrives, reconstruction is interpolation. We could recover the whole polynomial, but that is more work than necessary. The secret is f of 0, so we only evaluate the interpolated polynomial at 0. Lagrange interpolation writes f of 0 as a weighted sum of the observed y values. The weights depend only on the x identifiers. Here is the intuition behind that weighted sum. Lagrange interpolation builds one basis polynomial for each observed share. The first basis is 1 at the first x identifier and 0 at the other selected identifiers. The second basis turns on only the second share, and the third basis turns on only the third share. When we add y1 times the first basis, y2 times the second basis, and y3 times the third basis, the result matches all 3 observed points. For reconstruction, we only need those basis polynomials at 0. These are the Lagrange weights. Here is one calculation. For the first selected identifier, the other identifiers are 2 and 3, so lambda 1 multiplies the 2 corresponding fractions and becomes 3 modulo 17. Applying the same pattern to the other identifiers gives 14 and 1. The weights use only the identifiers, not the y values and not the secret. Now multiply each observed y value by its weight and add the results in the field. 10 times 3 plus 2 times 14 plus 15 times 1 equals 73. Reducing 73 modulo 17 gives 5. That is the original secret. The arithmetic looks small here only because the field is tiny. Real systems use much larger fields. For a real implementation, parameters matter. The prime p must be larger than the field elements you encode, and the number of shares must be less than p share identifiers must be distinct and non-zero. The threshold is a policy choice. It says how many parties must cooperate. Most importantly, every new secret needs fresh cryptographic randomness for the coefficients. Reusing coefficients destroys the privacy argument. In practice, you usually do not run Shamir's scheme directly over a large file. You generate a random symmetric key, encrypt the file with an authenticated encryption mode, and then secret share the key. This keeps the shares small, makes reconstruction fast, and lets standard encryption protect the bulk data. Secret sharing controls access to the key. Encryption protects the content. Shamir's scheme is elegant, but it is not the whole protocol. You need a careful byte encoding into field elements, metadata that records the field and share identifiers, and integrity checks so forged or corrupted shares do not silently reconstruct garbage. Avoid x equals 0 for participants. Avoid reusing random coefficients. And remember that basic Shamir sharing provides confidentiality, not automatic authentication or verifiable correctness. The complete flow is simple. Pick a finite field, put the secret at f of 0, choose fresh random coefficients up to degree t-1, evaluate the polynomial at non-zero x values to create shares. Later, any t shares interpolate the value at 0 and recover the secret. Fewer than t shares still fit every possible secret, so they reveal no information about which secret was chosen.